Hey everyone, ready for another deep dive. This time, we're tackling sentential logic.
Ooh, sounds fun.
Yeah, someone sent us this really interesting podcast episode called Connected Components of Chaos, along with some lecture notes, and I thought, why not dive in and see what it's all about?
So basically, we're going to try to understand how mathematicians figure out if a statement is true or false, right?
Exactly. But I gotta admit, when they started talking about truth assignments and tree structures for sentences,
hmm
I kind of felt like I was getting lost in the woods.
Oh, it's not as complicated as it sounds. It's kind of like, those true or false questions you get on quizzes?
Yeah, I remember those.
Well, it's like that, but we're going to level up a bit. In sentential logic, the basic building block is a sentence, and every sentence can be either true or false.
Okay, so true would be labeled T and false would be F.
Right, so like the sentence, the sky is blue, would be a T sentence.
Gotcha. So it's like a true or false game, but for mathematicians.
Yeah.
But what exactly makes it sentential logic?
Well, sentential logic focuses on how whole sentences connect to each other, not just the individual words within them. And to do this, we use special symbols, kind of like math operators, to link these sentences together.
Oh, I see. So instead of pluses and minuses, we have symbols for things like and or.
Yeah, exactly. Like we use the symbol S for ev, for or, for not, for implies, and S for is equivalent to.
Whoa, okay, that's a lot of symbols.
But once you get the hang of it, it's pretty straightforward. And with these symbols, we can build more complex sentences, called compound sentences, by connecting simpler ones.
So it's like building with Legos, using those symbols to snap different sentences together.
Exactly. And just like with Legos, the order and the way we connect them makes a difference.
Okay, that makes sense. So is that where atomic and compound sentences come in?
Yes. Atomic sentences are like the individual Lego blocks, the simplest units. They're single statements like, the sky is blue, or the cat is on the mat.
So they can't be broken down any further.
Nope. They're the most basic truths we have. Then we have compound sentences, which, well, you guessed it.
They're made by combining those atomic sentences, like
Yeah,
the sky is blue and the cat is on the mat.
exactly. And now get this. Every sentence, no matter how complex, actually has a hidden tree structure.
Wait, a tree structure, like an actual tree.
Well, not a literal tree, but a visual representation of how the sentence is built. Like, let's take the sentence. Ace D, D.
Uh-oh, there go the symbols again.
Don't worry, it'll make sense in a second. So the main connective, that first ace, it's like the trunk of the tree, and then it branches down to two sub-sentences, A, C, B, and D.
Okay, I'm kind of seeing it. So the main connective is at the top, and then the sentence branches out from there.
Exactly. And those sub-sentences can branch further, too. So A sum B would branch into A and B connected by another ace, and D would branch into A and D.
So it's like a family tree, but for the sentence. That's really cool.
It is. And these tree structures help us understand how the truth of the sentence is determined.
Wow, so we're taking these abstract symbols and giving them a visual form. But it makes me wonder, how does all of this apply to the way we use language in everyday life? Like, can we really use sentential logic to analyze regular sentences?
Actually, yeah, we can. The key is to break down any sentence, no matter how complex, into simpler sentences connected by our logical buddies. And, or not, implies, and is equivalent to.
Wait, so you're saying we can take any English sentence and turn it into a logical expression?
Exactly. Let's say we have the sentence, the cat sat on the mat, but the dog chased the ball.
Okay, so that's our starting point.
Right. We can split that into two simple sentences. The cat sat on the mat, and the dog chased the ball. Let's represent those with the symbols C and D.
So C is the cat sat on the mat, and D is the dog chased the ball. Got it.
Now, the word but here acts like and, right? So the whole sentence can be represented as CSD.
Wow, that's pretty neat. We've turned a regular sentence into a logical expression.
And this helps us analyze its truth. For CD to be true, both C and D need to be true.
So if either one of them is false, the whole thing is false.
Yep, it's like a chain reaction. If one link breaks, the whole thing falls apart.
Okay, this is making a lot of sense now. We've got our symbols, our sentences, our tree structures. It's like we're building a logic toolkit. But how do we actually figure out if those sentences are true or false in the first place? We can't just guess, right?
Well, there are no crystal balls in logic, unfortunately. That's where truth assignments come into play.
Ah, there's that term again.
Truth assignments are like setting up the rules of our logic game. We assign each sentence symbol a truth value, either T for true or F for false.
So it's like saying, okay, let's assume for this scenario, the sky is blue. So the sky is blue gets a T, but it's not raining, so is raining gets an F.
Exactly. And once we have these truth assignments, we can use something called a truth table to determine the truth value of more complex sentences based on their individual parts.
Truth tables. Now, those sound kind of scary.
Oh, they're not that bad. Truth tables are like a map of all the possible ways our logical statements can be true or false.
Okay, I'm kind of intrigued, but maybe a little intimidated too. I think we need a whole section just for truth tables.
You got it. Welcome back. Ready to tackle those truth tables?
Oh, I'm ready. Last time we were talking about assigning truth values to our sentence symbols, and truth tables sounded like a way to figure out, like, is the whole sentence true or false?
Yeah, it's kind of like we're setting up a lab experiment to test out different truth combinations, you know?
Okay, I can get behind that. So let's say we have those simple sentences from before. It's raining. We call that R, right?
Right.
And the streets are wet, which was W.
Yep.
So how would we build a truth table for the whole thing, for R and W?
It's raining and the streets are wet.
Exactly.
Okay, so first, we got to think of all the possible combinations of truth values for R and W. Each one can be either true or false, right? So we've got 4 possibilities. Both true, R true and W false, R false and W true, and both false.
Oh, I see, I see.
So our truth table would have like a column for R, a column for W, and then a column for the whole shebang, R to W.
Exactly. But how do we actually fill in that last column?
Okay, well remember, and statements are only true if both parts are true, right?
Right.
So if both R and W are true, R sub W is true. But if even one of them is false, or if both are false, the whole thing is false.
Oh, so basically RSGW is only true when both R and W are true. All the other combos make the whole sentence false.
You got it. Truth tables help us see all the possibilities and really get the logic behind these connectives. And we can do this for any sentence, even super complicated ones.
So no matter what crazy sentence we come up with, we can use a truth table to figure out if it's true or false, as long as we know the truth values of the individual parts.
Exactly. Truth tables are like the ultimate truth testing tool. But what if we want to compare 2 different sentences and see if they basically mean the same thing, even if they look different?
That sounds pretty useful. Is that where logical equivalence comes in?
Yep.
That's when 2 sentences have the same truth value, no matter what truth assignments we use.
You got it. We use the symbol "a" to show this equivalence. It's like saying they're basically twins might have different clothes, but they have the same DNA.
Can we go back to our rainy streets for a sec? Are there any sentences logically equivalent to RSW?
Let's see. One interesting equivalence is that the order doesn't matter in an "and" statement.
Okay, yeah.
So ASGB is logically equivalent to BRSA. So RSTW is the same as WR. The streets are wet and it's raining.
Makes sense. Doesn't matter which way we say it, the truth stays the same. Are there any other, like, really helpful equivalences?
Oh yeah, tons. There are these things called De Morgan's laws. They're super handy.
Okay, what do they do?
They tell us how to deal with negations. You know, those not statements when we're dealing with and or. One of De Morgan's laws says A as B as A as B.
Whoa, that's a mouthful. Can we translate that into English?
Basically, it's saying not both A and B is the same as saying either not A or not B.
So, like, it's not true that it's both raining and the streets are wet is the same as either it's not raining or the streets aren't wet.
You got it. See, De Morgan helps us simplify those tricky negations.
This is so cool. It's like we're learning a secret code for logic. But this all makes me think, can we use these equivalences to, like, debunk bad arguments or spot when people are being illogical in everyday conversations?
Oh, totally. Recognizing these equivalences can be like your superpower for critical thinking. Like if someone's arguing that because something isn't both A and B, then it can't be either one. You'll know they're wrong thanks to De Morgan.
So it's not just, like, theoretical stuff. It can actually help us be sharper thinkers in real life.
Exactly. But we've been talking a lot about individual sentences. What about when we want to understand how one sentence leads to another, like in an argument?
Yeah, how do we make sure our arguments actually make sense?
That's where logical implication comes in. It's about how the truth of one sentence can guarantee the truth of another.
So if we know one thing is definitely true, logical implication helps us figure out what else must also be true.
Yes, we use the symbol he to show this. Like R to W would mean if it's raining, then the streets are wet.
Okay, that seems pretty straightforward. But how do we actually determine this kind of relationship? Do we go back to truth tables?
We can, especially for simple stuff. But truth tables can get really messy when arguments get more complex.
Like with a ton of sentences and variables.
Exactly. Imagine a truth table with like 16 rows. No one wants to deal with that.
I can only imagine. So is there like a shortcut?
Remember those logical equivalences we talked about? They can help us simplify things.
Oh, so we can use those equivalences to transform an argument and make it easier to analyze.
Exactly.
This is amazing. Like we're building a whole logic system to understand how ideas connect.
We are. But I think we need to break down exactly how those equivalences can help us with logical implication a little more before we wrap up. What do you say?
Sounds like a plan. All right, so last time we left off with this idea of using logical equivalences to make working with logical implication easier. Feels like we're getting to the real nitty-gritty of how to analyze arguments.
Yeah, exactly. Logical implication is like the heart of argumentation, and those equivalences we've been talking about, they're like our secret weapons to unlock even the most complex arguments.
Okay, I'm all for secret weapons. Can we see how this actually works, like in a real example?
Sure. Let's say you're listening to a debate and someone says, if it's raining, then the streets are wet. The streets aren't wet, so therefore it's not raining.
Yeah, sounds pretty convincing, right?
It does, right. But let's break it down using our sentential logic superpowers.
Okay, let's do it.
First things first, assign those sentence symbols. Let's say R is it's raining and W is the streets are wet. So that first statement, if it's raining, then the streets are wet, becomes RW.
Got it. And the second statement, the streets aren't wet, would be W.
Right. And their conclusion, it's not raining, is R.
Okay, so we've got the pieces of the argument all laid out in our logical language. What's next?
Now, remember that equivalence we talked about earlier? AAB, AAB?
Vaguely.
Yeah.
Something about rewriting implications.
Yeah. It means any implication can be rewritten as a disjunction.
So we can transform RE or W into RE or W. So like either it's not raining or the streets are wet.
Exactly.
Yeah.
Now, take a look at what we've got. RE or W, and we know that W is true. The streets aren't wet, right?
All right.
So think back to truth tables. What has to be true for RW to be true if W is false?
Let me think. In an or statement, if one part is false, the other part has to be true for the whole thing to be true.
Yes.
So R must be true. It's the only way the whole thing works.
Boom. You just use logical equivalence to prove that the conclusion follows logically. If the streets aren't wet, it can't be raining. And we did all that without even using a truth table.
That's amazing. By using that equivalence, we can see exactly why the argument makes sense.
That's the power of these equivalences. They help us simplify things and see the structure of the argument more clearly.
I love it. It feels like we're not just like passively listening to arguments anymore. We can actually analyze them and see if they hold water.
Yeah, that's what's so great about sentential logic. It's like it gives you X-ray vision for arguments.
Wow. So we really went from these super basic symbols to breaking down real-world arguments. This has been an incredible deep dive. Any last words of wisdom for our listeners before we wrap things up?
Remember, sentential logic isn't just some abstract theory. It's a way to think more clearly and make better arguments. So next time you're reading an article or having a debate with someone, put on your logic goggles and ask yourself, are the conclusions really supported by the premises? Are there any hidden assumptions?
It's like we've unlocked a whole new level of thinking.
Exactly. By applying these principles, you can be a more critical thinker and a more effective communicator.
This has been an amazing journey through the world of sentential logic. Thanks for being our guide.
It's been my pleasure.